My name is Jamaica Marshall. I am the programs manager for Shadow the Scientist, and we are here with the amazing Dr. JD Armstrong from the Hawaii Institute for Astronomy to talk about this amazing interstellar object, Comet 3I Atlas. Very quickly, as many of you know, Shadow the Scientist is an initiative that's brought to you by a team, my wonderful colleagues at the University of California at Santa Cruz. Now, students, we're going to go ahead and jump right in with Dr. Armstrong, starting with an introduction. And after that, you're welcome to add your questions and comments in the chat at any time. As our last session, any extra questions that we don't get to, I will make sure that JD gets them so that he can answer afterwards. All right. So everyone has their questions answered. Thank you so much. And without further ado, the amazing JD Armstrong. Welcome, JD.
Welcome. Hey, it's good to see everyone. Aloha.
Now,
All
JD,
right.
you're joining us from, so I'm on the Big Island of Hawaii in Hilo, which is the east side of the Big Island. So Mauna Kea, I just came from outside. Mauna Kea is rising in the background. It's beautiful. And we are just about to finish nighttime observing here. But you are on Maui, and Maui has a totally different mountain with observatories on it. Can you lay the groundwork for where you are with us, JD?
So I'm on Maui, which is the next island over from you. And I'm in actually sitting in my home in Kihei, which is kind of on the southern part of Maui. And yeah, we have a number of telescopes up on the summit of Haleakala. Uh, and those are, I'm sure, finishing up observing. Well, most of them are finishing observing, but one is actually going to get ready to start observing. We have a solar telescope over here, a telescope dedicated to the study of the sun. The Anoa Solar Telescope is the world's largest and most advanced solar telescope in the world. So, that cover what you wanted?
That is. Thank you for laying the framework for us so they can help to visualize where we are joining them from. Yes, thank you. And I believe students, if you get a chance, we'd love to know where you're joining us from. I assume that you're all in India, but maybe where in India are you? Would love to know. All right, JD, get us started. Now, this interstellar comet has been everywhere. We've had three sessions on it with Shadow the Scientist, one that got lots of media attention. We're seeing our one of the images from our Shadow the Scientist session with Dr. Karen Meach from the University of Hawaii at Manoa. We're seeing that all over the internet. It's thrilling and exciting. What's so interesting about interstellar objects, JD?
They're new. I think that's one of the big things is that they're kind of new, and um, we've only seen three of them, and so it's exciting, and in addition, they're from another solar system. This is a way for us to learn about other solar systems in a little bit different way. One of the things that I've thought about, started thinking about with Oumuamua was that the newest discoveries usually comes from the new wavelength of light or the new information carrier. Well, in this case, with these interstellar comets and interstellar asteroids, the carrier for the information for the majority of the distance is macroscopic bosons, or it's macroscopic physical mass, and so that's unusual. It's a new thing for us, and so um, each each one is really exciting because we really don't know what we're going to see. We can guess, but when it comes down to it, it you know we could find something really unexpected.
Oh, I love it. And definitely we have in our previous session, we saw, so kind of our first session with Dr. Bryce Boland at Keck Observatory, we started to see like
Mhm.
just uh, bits of a tail starting to form. And over a month later, by the time we're using Gemini South in Chile, we see, I think, traces of CN. And the spectra of this comet.
Mhm.
So it's just constantly evolving, and it's gotten very large. But now it's heading towards what towards perihelion. JD, can you tell us what perihelion is, and maybe then you can also get started with some observations. I think you're gonna possibly see if we can get.
Yes. Okay. So the we'll do a little bit of a teaser on that. I thought it would be fun for us to take to program some observations on the Las Cumbres observatories, and if we are lucky, we might actually get to see the observations by the time before we're done with the session. So, if anyone knows of a good target like maybe a Messier object that they would like to take some images of, let me know because those we could try for that. Um, and so perihelion. Okay.
Yes,
Um,
perihelion.
Yes, para means close and helion means sun. So this is the point of closest approach to the sun. This is as close as the object is going to get to the sun. And that means, of course, it's hard for us to observe because if it's close to the sun, it's up during the day instead of the night. But we'll see what we can do. I've got some observations that were taken a couple months ago, not long after the discovery. So,
Oh, that's exciting, JD. Will
yeah.
we be able to see some of these images?
Yes, I've got some images and also spectra. So, all right, shall we get going on? Does anyone have know of anything that's up that they might want to observe?
I do, but I don't count. Oh, Manisha, yes, ma'am. Do you have a suggestion for us, Manisha? And students, you can put your suggestions in the chat here. What Messier object would you like JD to submit an observation for? And
Or asteroids, or maybe even a planet?
ooh,
Yeah,
astro or planets. Oh my gosh. So let's give the students
just
a few minutes to maybe answer. And JD, what if we come to a consensus on what to submit an observation for? If it comes in, if the image finally comes in, but it's after we end the session, will I still be able to share it with the students?
I will make sure to send that to you. You know how to get hold of me and remind me about things like that. You're wonderful in keeping me on task because you know how absent-minded I can be. And yes, we will take. I'll send the images to you, and if they don't come in with our request, I'll just refresh the request until we do get some.
Thank you so much for that, JD. That is
Mhm.
amazing. Okay, so students, for the observation request, it can be a Messier object, it can be a planet, it can be an asteroid, anything that you find interesting. Go ahead and put those suggestions in the chat, and I'll be looking for those throughout the session. And also, as you put questions in the chat, I will put a little red question mark by it. For one, that helps me in the transcripts afterwards to pull out all the questions to make sure that if it wasn't answered, I add it to a list for our science host to answer. And also, it helps it to be easier for me to track all the questions too. So that's why the little red question mark is there. All right, back over to you, JD.
Okay, I'm seeing some comments in chat.
Yeah.
Oh, Hercules, globular cluster, Andromeda. Let's look at this first one. 2025 TQ5 seems close enough to observe at the moment. Let's take a quick look at that.
Oh, the
See
pillars are
what we
pretty.
can find. I'm going to copy this.
Ah,
Wow, these are great suggestions. I'm quite impressed. So This is an asteroid. The place we want to go is the Minor Planet Center. And
Mm-hmm.
let's just really quickly take a look and see how bright it is. One of
Mm-hmm.
the things when we're observing an asteroid, one thing we want to consider is how fast is it moving? And another thing we should consider is, um, sorry, trying to talk and type at the same time. Another thing
Can
we
you
need
share
to
your screen
consider is
with
how
us?
bright it is. Pardon? Oh,
Can you
yes,
share?
thank you. Uh, hopefully, yeah, let me.
Ooh, and the Sombrero Galaxy. Gosh, I've imaged probably half of these myself. Hercules is one of my favorite ones. M13. Yes. In fact, I think I imaged Hercules probably 4 or 5
Mhm,
times already in the past month. It's one of my favorite. This is an open cluster. Oh no, globular cluster
mhm.
for M13, right?
Yeah, yeah, I believe so. That's great. Great suggestions, everyone. Thank you so much.
Yes.
Okay, so 2025 TQ5. Um, so the magnitude is 18. It is moving really fast in the sky. And so this is actually going to be probably too faint considering how fast it's moving for us to get with these telescopes. We're using some of the smaller telescopes on the Las Cumbres Observatory Global Telescope Network. We might try with the 2 meter if we have something that's really particularly good. But the fact that it's moving 110 arc seconds. Let me get a pull up paint here. Okay, so basically, what's happening is we've got this asteroid, and I'm going to draw it as I'm going to do this. I'm going to there. That's the night sky. That looks better. And what we have is we have this asteroid. Okay, and it's moving very fast. So instead of getting a single point, if we look at the same spot in the sky, we're going to get this. We're going to get it. It's going to be smeared. It's going to be like instead of a dot, it's going to be like that. But the problem is we have to take a long enough image to actually see it. And if we smear the light out like that doesn't really help us see it too much. And so it's just kind of moving too fast for us to see, but really great suggestion. So full credit on that.
All right.
Um, so let's go to the next one on the list. That was a good one, but we unfortunately just can't get it. And where's my comments? Jamaica, what was the next one? If you could,
Here.
please.
The next one, oh, so you were looking at 2025 TQ5. The next one I have is the Hercules cluster from Krishna.
Hercules cluster. Oh, that's a young open, that's an open cluster, isn't it?
Yes, yeah.
Yeah. I, yeah, I'm going to look this up on Wikipedia. Wikipedia actually tends to be a very pretty good place to look for things.
Mm-hmm. Ooh, pillars of creation.
Um, yeah, Hercules cluster.
Okay.
Oh, it's the Hercules cluster of galaxies.
Oh, the cluster of galaxies. I was thinking about
Is
the star cluster. Okay.
okay. Yeah, maybe. Yeah, but I'm guessing. Oh, oh, so Messier 13, the Hercules. Okay, is this the one that you meant?
I think so. That's the one I thought when I
Okay.
saw what Krishna put in. I thought this one because I just did an image of M13 myself. I love it. It's beautiful. It's exactly what I think about for a star cluster.
Yeah, it's a really nice globular cluster. That's great. Let's try that. It might be a little bit close to the sun. Right now, the right ascension of the sun is about 13 hours. So we might be able to squeeze an observation in.
All right.
Okay.
And now what we're seeing on
And
the
Shadow
screen
the scientist.
is
Yes.
this
Oh, this is the observing portal for Las Cumbres Observatories.
right?
And you need an account to submit observations, but they do have a global Sky Partners program that, like, your teacher could submit a proposal, might be able to get some time. They're really good about that. And another upcoming network of telescopes is the Photon Ranch, which is run by Wayne Rosing, who's the founder of Los Cumbres. Okay, so we want to see if we can get Messier 13. The request name is just some name for the request so that we remember what it is. I'm going to put in Messier 13 and STS for Shadow the Scientist. That way, when I look at the list of observations, I will know whether or not um, I'll know exactly what this is without having to look at it and think about it.
Wonderful.
Now, let's see, configuration. We're going to be using some of the small telescopes because they are really quick on turnaround time. Um, this is a globular cluster, so I'm going to guess maybe about 180 seconds. Now, usually I ask, do you want black and white or do you want color? I know you're muted, but everyone yell out, do you want black and white or color? I'm not seeing you yell. I can't see you. Do you want black and white or color? Come on.
Let's see. Put those in the chat for me. I'm gonna vote for color. Does my vote count? Color.
Even
Yes,
I want
everyone's vote
colored.
counts.
Yeah, yes. I
Nidhi
think
says
Yeah.
color.
most
I
of the responses are for colored. Yes.
Everyone says
okay, yeah, I figured it would be color. Everyone I've only had like one or two
Okay,
in several
somebody has
years of
written the
doing
world
this.
needs color, I think, if I read correctly.
yes,
Yes.
Who is
yes.
that? Neeraj. The world needs some color, guys.
Oh,
Love
yes.
I really like that,
Okay.
Neeraj. Yes.
So, this is a really good intro to some of the things we're going to be talking about when we get to 3I. Our eyes see sort of in three bands of color. Your computer screen have you heard of RGB, red, green, blue color screens? Okay. That's because our eyes kind of have three color filters. They see red light, green light, and blue light. They can tell the difference, your eyes can tell the difference between those three colors of light. So to tell our eyes what color something is, we need to have a measurement of the blue, the red, and the green. And so we're going to take a blue image. We're going to take a red image. So this filter here, this is a Bessel B as in Bravo filter. That's a blue filter. It's like a blue piece of glass that we put in front of the camera when we take the picture so that only blue light gets through. Then we're going to take a Bessel V as in Victor filter. I tell people that V stands for Viridian, but that goes back into a little bit of history of astronomy. And then so we've got a blue, we've got a green, and we need a red filter. Okay. And we're going to type Messier 13, and the system actually will look this up. If the object is fairly well known, it'll usually find it for us. And we can get that. Okay. So we don't have, it's not going to happen real soon, but let's program this in and maybe do one more that we have a chance to get the observations with before we're done.
Okay.
So, okay, what I'm seeing here, this is the visibility chart. Left and right is time, so 1600 hours, and this is universal time, so it's like Greenwich Mean Time without doing any adjustment for daylight savings. And then up and down is kind of like how far up or down in the sky we're looking at. So up is looking straight up, and then we get closer and closer to the horizon. And when there's a solid line, one of the telescopes on the network can observe. So somewhere between about 19 and 20 hours universal time. That's in another 4 hours. This can be observed from this site, which is the Canary Islands. It's Tenerife. It's a very good site. And then from McDonald Observatory in Texas, and then from my favorite, Haleakala, but that's not until tomorrow night. And so let's go ahead and put this in. We'll submit that request. It'll take about 10 minutes of Wayne's telescope time. Wayne's a nice guy. I'm sure he won't mind. And so we've gone ahead and submitted that. All right.
Mm,
We,
awesome.
should we try? Should we try? I think Andromeda was the next one. Was that
Yes.
correct?
Andromeda was the next one. And before we move from this one, we had a question.
Mm-hmm.
What does, excuse me, what does 1.5 indicate? It was on the last screen. And where did it go? 1.5. Is that maybe it's the IPP factor? Perhaps that's what the
Is
question was
that
about.
it?
Yeah,
Um,
in the graph
wow.
at
Oh, in the graph.
yes.
Oh, 1.5. That's like how
Thank you.
far up and down, and it's measured in weird units. It's called air mass. When you're looking straight up, you're looking through the least amount of air. Okay, think about um, sitting maybe at the bottom of a swimming pool. So the ground is here, the top of the air is up here. If I look this direction, I'm looking through very little air, but if I'm looking off in that direction, pretending that that's a straight line, I'm looking through a lot more air. The more air that we are looking through, the blurrier the image. So the smaller the number, closer to one that is, the better the image will be. But as long as it's not below about 1.5, it usually tends to be pretty good. So very good question.
Mm-hmm.
Wow, this group is awesome.
Yeah, it's true.
All right. Okay, so we'll really quickly program in Andromeda. IPP factor is just a priority thing. Bookkeeping, don't worry too much about that. And we're again going to do color. Does everyone want to do color? Yes.
Yes, we all
I'm
want
psychic.
color. And we
Yeah.
have a question about what about cadence. What does cadence mean, JD?
Oh, cadence. If you
Mhm.
want to, that's a really nice feature that this observatory has. And what it is, sorry, typing and thinking or typing and talking at the same time isn't working for me. Um, cadence basically means take multiple sets of images. So maybe I want to observe a supernova, which we're actually observing some supernovas, and you want to observe it every day. You can just say, hey, give me a cadence of 24 hours, and then you set the window large enough that you'll go for however many days you want, and it'll generate multiple observation requests. That's really good. All right. Okay, this won't be done until after we're done as well. But I do have an older picture of Andromeda, and why don't we do this? I'll submit this. Oh, I forgot to put Shadow the Scientist
I was gonna
right
ask.
there. Good, good. Okay, so we've got Shadow the Scientist in there. This will take about 10 minutes. That's not a lot of time. I think that's great. Everyone ready to submit?
We're ready.
All right. Okay, so we just submitted that.
Oh, that's
All right, so we've talked a
exciting.
little bit. Hopefully, I've submitted that. Ah, there we go. Okay. Oh, there's my chat. I can grab chat and bring it down here. Okay. So, wow. Wow, these are great questions. Okay. What I'd like to talk about a little bit now is Oumuamua, or is 3I. 3I. So we don't really, it's really hard to get a spacecraft out and get samples on it. So we really have to rely on colors. And so usually I have my dad's ring and I'll sometimes hold it up. And it's a turquoise ring. So pretend I'm holding up my dad's ring. It's in the other room. And it's a silver ring with a piece of turquoise in it. Okay. And if I'm holding up my ring and I say to you, is this a gold ring? What are you going to say? You're going to look at that and you're going to say, no, that's not, because it doesn't look. Should I let's do this. Give me 1 second. Thought of this. I can still hear, so we can still talk.
Perfect. Thank you. Well, I will say, while JD is coming right back, these are wonderful questions. Thank you so much. Keep them coming. They're
No.
amazing. And I will make sure we get to them as many as possible. Oh, and JD is back. Welcome back, JD.
Okay, I'm going to stop sharing so that we can see. Here is my dad's ring. Okay, can everyone see the ring?
Yes. Oh, there it is. Uh-huh. Yeah, yeah.
There's
I see
dad's
people
ring. Yeah.
nodding. I see people
Okay.
nodding their head.
All right. So you've never been anywhere near this ring, but is this a gold ring?
Um, I don't know.
Okay.
Manisha,
So
can you
most
tell?
Uh, I think I don't know. Oh, I'm so sorry. I think I had some uh video issue here. I don't know what happened, but I think it looked like, I don't know, silver or platinum. Doesn't look like gold. Looks like
exactly. It
platinum
looks
or
like
silver.
silver. Yeah. It is in
Mm.
fact silver. But how do
Oh,
you
okay.
know it's not gold? That's exactly the right
Uh,
answer. That's what I was hoping for.
yeah. I think
You said it doesn't.
familiarization with how gold, silver, and like they look like in color, and like, because the color is the only thing which we can look at virtually. We can't touch
Right.
it, or we can't like smell it or something. So yeah.
Yes. Right. Color. There's the word I was looking for. Okay, let's see if I can find where to share my screen. And I'll go back to sharing my screen. That's exactly right. And so even though you've never really, seen this ring, even on a video of this ring before, most likely, you can tell me, JD, that's not a gold ring, that's maybe silver, okay? Just by the color. Now, it's a little bit of preview of what's called a priori information. You know it's a ring, and so you know materials it is likely to be made from. Okay, so you can eliminate a lot of things that are kind of whitish color. But by looking at the color of the ring and using other information you can actually tell what this ring is made of. And that's what we do with asteroids and comets. And so let's think about this for a minute. Now, one thing I was noticing is, okay, this is not quite the color of my skin, at least not what I'm seeing on my screen. Okay, I seem to be getting bit of extra blue in here. So this is a perfect example. I'm loving this. Okay. If I get closer to the screen, yeah, you can definitely see some blue in my face, right? Okay. So, well, what's happening is my face is looking blue because it's got some blue light from, I'm guessing, from right there on my screen. And so that makes my face look blue. We don't really want to know what color it really looks. We want to know what color it is. So there's two things that are going on. One, there's the actual color of the object. And two, there's the color of the light that we place that we're shining on the object. Okay. And in the case of this of of 3I, that's sunlight. And let's think about this for one more minute. I've got this here. Okay. So the reason this spot here looks blue is there's more blue light coming from that spot on your screen. And this little red light. Okay, makes sense? So we're going to pretend that we're shining this on a piece of paper, okay? Or a projector screen instead of your display screen. Okay, what color is the screen? The screen would be white, right? And it
Mm-hmm.
looks white when we shine white light on it. But and I do this with a projector screen, um, and then I come over here and I say, now what color is the screen? Well, it looks blue, right? But it's still a white screen. Does everyone follow kind of what I'm saying? Are your imaginations clicking with what I'm talking about?
I see nods
Some of the students.
and thumbs ups.
Okay, good.
Thank you.
All right, good. Thank you. Okay, so basically, we don't want to know what color it looks. We really want to know what color is it. Okay, that's what can really tell us what it's made of. And so what we need to do is we need to figure out if what color the light shining on it is. If if we have twice as much blue light, then we need to know that. And when we're talking about those blue colors, we divide it by a factor of 2 to even it out. Okay, does that make sense? Okay, so let's jump into a little bit of the data here. We're looking at this. Let me see here. Here it is.
And we have a
Okay.
question too, JD, that's I think related.
Mm-hmm.
And this is what's the minimum size object that can be tracked with, let's say, Las Cumbres Observatory?
So probably that's in relation to the asteroid that we're looking at.
Mm-hmm.
We actually observed a 2 meter asteroid before it impacted Earth. So this was an asteroid that hit the Earth, and I was working with a friend of mine, Dr. Marco Michele, who's in Italy, and basically we were actually able to observe this asteroid before it impacted. And so that was really cool. So 2 meters, we can actually observe, if the conditions are right, we could observe something smaller. Yeah. What really is important is how bright it is. Bigger objects are going to scatter more light, they'll be brighter. But also lighter color objects make it easier for them to see. So it's a complicated question. If you want a simple answer, go with 1 to 2 meters for something in space.
That'll work. That'll
And
work.
real quick, one more thing I'll show with this. In I can find it real quick, is
Oh, wow. We can see all your beautiful images.
oh yeah, yeah. Yeah, if you want some of those, I'm more than happy to send them. Here's a pretty good example of how small an object we can see. Does everyone see this moving object here?
Oh, oh, I see
That
it.
is a car. Yeah, let's
Is that the Tesla
okay
car?
right there. That is the SpaceX Tesla. So it's really a rocket body attached to the car. And the line, remember how I was talking about streaking the image? The exposures were longer than they should have been, so we get a streak instead of a dot moving around.
Oh, oh, that's awesome. Yes, I'll request this one
All
for you
right.
to share with them.
Yeah, I will be more than happy. That's one of my favorite ones. I'll probably send a picture of the students whose science fair project uh, that went into. Okay, so real quick, let's take a look at some actual images of, sorry, typing, of the comet. And these were taken from Australia. Again, the Las Cumbres Observatory network. And I'm going to open one of these.
Oh, we have a
There we
question,
go.
maybe.
Okay, go
A
ahead.
quick question here is, so just to clarify, so the long exposure creates an average of the positions, and is that what makes a streak instead of a dot?
Yeah, that's a good way of looking at it. I would not have thought of it that way, but it's kind of an average of the positions throughout the. I really like that analysis. Yes. All right. So I'm guessing it's probably that. I'm opening up Astrometrica right now. This program will help us load multiple images. And let's see here. Let's try these. The instrument that we took these images with uses four four filters. So you get a green, a red, an infrared, and a further infrared. So an I band and a Z band. Those are both infrared. Um, and you get them all together at the same time, which is really kind of cool. Um, and so we've got about 8 images. I think I loaded 7. We're going to go ahead and blink these, which means play them like a movie because the asteroid is, or the comet is moving in the images. Oh, yeah, there we can see it. Okay. And yeah, I would say that there's a little bit of fuzz around that. That is a little fuzzy. So and these were taken in July 28th. So already we were seeing fuzziness. And this moving spot, that's our target.
Can you
All
put
right.
a circle around that? Oh, just
Um,
right there. I'm just making sure everyone catches
yeah,
it because it took a minute for me to catch it.
here. Okay, let me do that. It'll take a moment. Gotta switch this. I'm gonna try to do this. I just have to change the configuration and actually get okay, and since we're gonna do that, let's look at a different band. Why
Mm.
not?
And does a
So this is
different
like a different color.
filter? Ah, different color, yes.
Yeah, it's different filter. So yes. And this time we're going to tell the program, don't blink it, but figure out where everything is in this image very precisely. And then we'll blink it and I can put a circle around it.
Thank you, JD.
Uh-huh. Okay. Okay, that means it figured out where all these stars are. It looked at a catalog of stars and was able to find a match that made sense. I'm gonna
Ooh.
blink this. Okay, there we go. And this right here, that is Three-Eye Atlas.
Oh, wow.
And you can see, okay, look at how the light is kind of spread out. This is a graph of how bright it is compared to the position. So left and right is like the position in the image, up and down is how bright. Look at how this is kind of asymmetric and it's kind of smeared out a bit. Okay. Compared to a star, let's choose a star that's comparably bright. This is a little bit brighter. That's not as spread out. It's a little bit spread out, but not as much. So we were just beginning to develop kind of a coma at this point. So the fuzzy atmosphere around the comet. All right, so there we go, and we can well, move this out of the way,
Oh,
and we
JD.
can just go ahead and mark these. Yes.
You. Um, I put a link to Astromatica in the chat just a little bit ago when you first opened it and told us about it. But some of the students have tried to download it and it's not working. I think we encountered this issue before, and you had a solution.
Um, I don't know. I'll have to check the link. Another good program that we actually could do this with is called Astro Image J, and that's totally free. So
Ah,
Astro Image J, um, it's
okay.
sometimes a little bit troublesome because it runs with Java, but it'll run on any computer. Oh, it could be that Astrometrica only runs on PCs. It does not work on Mac or Linux. That might be the
Oh,
problem.
okay, so
Yeah.
that's one potential issue with Astrometrica. Okay, so I'll put a link to Astro Image J in the chat as an alternative to Astrometrica. Okay, thank you, JD.
Yes. Yeah.
And then
And there's
Manisha
some
says,
good YouTube videos.
okay, and Manisha
Pardon?
says it's working for her, but it does say that it's insecure. Yes, yeah, and someone else says it's working for them too. And all right, so
Okay.
I'll put an alternative link in the chat, Astro MSJ. Okay, sorry, JD, thank you.
Okay, great. No worries. Yeah, this is great. Good question. I really like this group. You really have some good questions. Thank you. It's really nice to kind of have a little bit more dialogue. Sometimes I feel like I'm just talking into a void.
I'm
So
always here, JD, you know.
you're always there. Yes, that's true. You're always there, but it's sometimes, but I'm trying to talk to the students, and so it
That's
kind of,
okay. That's
oh, and so, okay, well, there you go. These are images. And what I'll be doing with these images is I'll be measuring how bright it is in each color. And then I also have images of a star that has the same color as the sun. And by dividing how bright the asteroid is in the images by how bright the the star is in each of in the same filter, that'll divide out the color of light that's shining on it. And also, maybe the telescope is more sensitive to red light, which it actually is, Okay. If it's more sensitive to red light, it's like it's got red colored sunglasses on. Okay. By dividing by the uh, a star that is the same color as the sun, we correct for that sunglasses effect. We correct for um, the color of light that's shining on it, and we get really just how reflective the object is at each color. Okay. How reflective an object is called albedo. And so what we're measuring is something like a spectral albedo. Okay, this would give us a 4-point spectral albedo. How about this though? Since we've already gone beyond how many colors our eyes can see, how about we go up to about 4,000 colors? Would that be kind of cool?
I mean, I think
Yes,
so,
Katie.
Anisha. What do you think? 4,000 colors? Yeah.
Okay, these are images that were taken. They use a spectrograph, and what the spectrograph does is it takes the light from the comet and it spreads it out into a rainbow. And that way you can measure how bright it is at each color on that rainbow. Does that make sense to students?
Yes, we're getting some thumbs up.
Yep. Okay, and so let's look at some of these. Yeah, sorry, I'm craning my neck because I'm looking at a screen up here. Um, okay, so this is kind of one of the images that we get off of this. Let's close that. Okay. This is another free program. This is SAO Image DS9. So right here, this band here, it's pretty fainted. That is the light from the asteroid, from the comet, and it is spread out into its colors. And so you can look at the wavelength right here where it says WCS. That'll show the wavelength. This is 6,833.6 angstroms. Okay, so that would be, I think that'd be red. If someone wants to do a Google search, you could check me. 6,600 angstroms, I think would be about red to our eyes. But this shows basically what we could do then is we can measure how bright this line is at each point, and then we get a measurement of how bright it is at each color. And we could get like thousands of colors. So I've converted these images, into they did the extraction. They measured how bright that line is at each wavelength. And then I've converted these into .csv files so I can throw it into a spreadsheet and show you this. Give me a second. Okay, there we go. All right. So here's the wavelength, and this is the flux. Flux is the brightness, how much light we're getting. And let's make a graph of this. So real quick, there we go. XY scatter. And this is 3i, x-axis.
I really appreciate that we get to see you using actual data from 3i. Oh, I see we have a question. Can you put your question in the chat, please? Thank you.
Yeah, there we go. Okay, and I'm going to, this part of the graph for some reason is not working very well. So I'm just going to kind of cut that out so that we can look at the good part of the graph. There we go. So that's the spectrum of 3I. And I'm going to make the dots a little bit smaller. What you're seeing is there's a fair amount of noise. It was kind of faint, as you saw, and so the measurements are uncertain. Okay, so it bounces around. So there's somewhere in here, there's a line that is the real spectrum, and then it bounces around from noise. Okay, so
I'm
one thing we could do is we could add a bunch of spectra together. And so let's look at these spectra because I took 8 different spectra. This one looks good. The reason I did 8 spectra instead of doing a longer integration, which would collect more light, is this is in a very dense star field. And so the comet might run over a star while we're watching it. And if that happens, then we don't want to include that because those images because it'll they'll be kind of bad. So this is number 1. That looks good. Opening number 2. That's pretty good. Opening number 3. And we're pretending that I haven't done this before, right? I'm
well,
sure
it's
the
new
students
for
have
us.
figured, yeah, I'm
It's
sure
new.
the students have figured out, yeah, he's looked at this data before. All right. Okay, so here we've got it ran over a star. So for this one, we would not include it.
Okay.
Okay, so do we want to go with, okay, I have a Python program that I run. Show you the Python program. Well, I won't actually run it because I've already done that. But it's basically what this does is this takes the spectrum from our asteroid. It takes all these spectra images and I filter out the ones that are bad, like I would not include this one. But it takes all of them, adds them together, and then also takes the spectrum from a solar analog and divides that solar analog. And then it gives me this nifty little spreadsheet here. And it's opening, really, it's opening. Okay, so this tells me the files that are used in this, and this is the solar analog file, so that if I can go back later and say, hey, was that the right one that I wanted to use? And it also has the name of the object, and then here's the wavelength, and this is the albedo, the spectral albedo, the how shiny, how bright the object is at each color, at each wavelength. So we can go ahead and make a graph of this. And here's graph. And XY scatter.
And
Okay. And again, below 5,000 angstroms, apparently there was something wrong with the instrument that day. So we are going to just kind of cut that out on this graph. And it's thinking, there we go.
wow.
Okay. Now
Mhm.
this spectral line, this really bright spike here is called the spectral line. That is probably due to the fact this this comet is moving so fast, we're seeing a little bit of Doppler shift on it.
Really? Doppler shift. So since it's coming
Yeah,
towards the inner solar system, so would that be blue shifted?
that's right. It would be blue shifted. So this is, if you hear a siren on a truck driving past you, right?
Mm-hmm.
When it's coming towards you, it's higher pitched. When it moves away from you, it's lower pitched. Light does the same thing. When it comes towards you, the wavelengths are compressed a little bit. They're a bit shorter, and so it's a little bit bluer. So shifted this way. When it's moving away, it would be shifted towards the red, longer wavelengths.
Longer
All
wavelengths.
right,
Oh,
so there we go.
okay. So JD, I want to be super respectful of the students' time because it's evening time for them and they do have school the next day. We have about 3 minutes left. Lots of questions here. So first, can I please ask, could I possibly
Mhm.
request the data that you just showed us? Could I request this data from you and some of the images so that if the students want to try this themselves with Astroimage J, Astrometrica, or
Yeah.
anything, they could do that? Okay. So I will ask you
Yes,
for,
can do.
thank you, JD.
All right. And while we're going through questions, I'm going to compare to a couple asteroids.
All right, sounds good. Let me hit, we have 3 minutes. So let me start with the last question first because it's relevant to what we're looking at here. So the noise changes pitch as it passes you, as what Abby was saying when we were talking about Doppler shift.
Mhm,
So another question here is, what are differences between flux, like flux, IRAF, and then the other columns
mhm.
containing flux values?
It was a different way of extracting the spectrum. In other words, calculating how bright it is based on that image, based on the image of the spectrum.
Okay. And
Okay.
then we also had a question. Is there any other open source data that we can use with this that you can recommend for us?
Open source data of 3i, not that I know of, but
Not yet.
I'll give you some. I'll share with you some of the images I've taken, and since you are STS fans, I'll even share the. I'll send relative spectral albedo of both 3i and uh, these three asteroids, Psyche, Hanukkah, and Themis, as well as a
Whoa!
comet, so that you can compare for yourself and see which one is the best match. Which one did you think was the best match? I think it's
Ooh,
the comet.
you think it's the comet? Oh, that's so
Yeah.
exciting. Okay, so I know Manisha's gonna make sure that I send her this data for the students. Wonderful.
Okay.
And in our
Yes,
last,
I
Okay. And
will
I'll
be
have to
following up with you a lot.
yes, for sure,
Yeah.
please.
Wonderful.
And in our
Yeah.
last
I
minute,
will need to reprocess the data. But yes. Okay. Go ahead. Yeah.
thank you, JD. And in
Yeah.
our last minute, could we go back and check on those observations that you submitted earlier to wrap things up? And I don't know, Manisha, I think we need another session with JD.
Yeah,
That
I
would
would
be
love
fun.
that. Yeah, I think students would love to have that session again. Yeah.
Okay, awesome, awesome. All right, so this is
All right.
Andromeda.
Andromeda is on the schedule for at Tenerife, that's Canary Islands, for 2003, and it's now 1600. So it's
Okay,
about 4 hours from now.
okay.
And M, our Messier 13, also for Tenerife, that'll come in just before that.
Okay. All right. Sounds good. So then, yes. So Manisha, once these images come in, JD will share them with me. I will share them with you for the students, and they will have, like, this is so special to have
Yeah.
observations that they contributed to actually share with them. And this will be their own on images that they can download and everything, which is going to be
Mhm.
awesome.
That would be great. Thank you so much for this. Thank you.
All
Awesome.
right. Well,
By the
thank
way,
you. I really appreciate it. Go
I
ahead.
couldn't help but like just say that Advaita is asking you that is it cool sharing a surname with Armstrong?
Yeah, I'm no relation to Neil Armstrong, but yeah, it's my name. I kind of like my name.
We like it too. We like it too. Well, JD, this has been absolutely fantastic. We're definitely going to request another session with you. And certainly, I know the students will be looking forward to getting answers to questions that I wasn't able to ask. I didn't want to stop you too much, so I'll share those with you.
Mhm.
Of course, we'll be looking forward to getting the images and the 3I data that they can actually play with, which is going to be so fantastic.
All right. Well, thank you all.